All right, hello everyone. Welcome to the DeCal. Can everyone hear me?
Yep.
All right, great. So during today's lecture, we invited a guest speaker, Dev, and he's going to talk about zk-SNARKs and other related application of it. So Dev, would you mind do a brief introduction about yourself?
Hey, I'm Dave. I work on blockchain scalability and SNARK research. Yeah. Okay, so are we good to go?
Yep.
Okay, so let me figure out how to share screen. Okay, presumably you can all see the screen, or?
Yep.
Okay. Cool. So disclaimer, this presentation was written very hastily due to, just complications due to the virus. Hope everyone's doing okay due to that. And please stop me for questions. This talk may end kind of short if you don't. A lot of the value here is asking stuff. Okay, so SNARKs and scalability. First, blockchains are slow. This meme you may or may not have seen before. Someone's trying to buy coffee with Bitcoin. They have to wait all day because of many confirmation times, like several hours worth. So what are the bottlenecks in scaling? Okay, presumably you guys have some ideas for this. Any example problems with scaling a chain? This isn't a trick question.
So there's increasing the block size, reducing the block time. That's all I know.
Yeah, exactly. So that's two of them. Okay. Yep. Any other ideas? One second. Having some weird problems with Zoom. Oh, L. I didn't think that through. Well, any other ideas now that you've seen the entire slide? But yeah, block time and block size are totally two of them. So here's a quick list. So block time would be consensus time. Like both time to consensus time's two parts. One is block time, and then time to finality. These are actually distinct things. So in Bitcoin, block time is 10 minutes, and then your time to finality is hours. People throw around 10 blocks. In proof of stake, both of these sort of mitigates this. Both of them are much smaller, like 5-second blocks and 5 to 10-second finality times. And then block size is a bandwidth problem. And like you can only have so much data per block because this data has to go out to the rest of the world very quickly. So the other things that you may or may not have realized about blockchain scaling is you have limited computation. So in Bitcoin, you have 7 TPS, something like that. Ethereum, similarly, 15, 20-ish, a tiny amount. And there's a fundamental problem here that everyone has to redo the computation. You have, and in Ethereum, it's Turing complete. So also, if you're sending chats that are questions, please just say them out loud. Mostly because due to some weirdness in screen sharing, I can't actually click those and go through it. Okay, so here's a computational load. Ethereum's Turing complete, and so you can express any computation, but only up certain many VM steps. So the reason you have a limited number of VM steps is due to just you can't put more into a block. Then there's some other issues are I/O. Like in Cosmos, the main time sink per block is actually I/O operations. The amount they have to write to disk.
Dave, I think our slides are all stuck on one thing right now.
Oh,
we can't see anything. It's kind of weird.
Wait, can you see bottlenecks and scaling and 6 blue boxes?
No, only just the title slide without the
Oh,
6.
wait, what? Okay. Do you see anything right now?
Yeah, now it's at that slide.
Okay.
Works.
Let me try stop sharing, then I'll try again. I'll just share my entire screen, not a window this time. Might just be easier.
Yeah, hopefully.
Okay, well, that's unfortunate. There was a relevant. Do you see this now?
Yeah,
this-
yeah. Now it all works.
Okay. Cool. Thanks, Ishan.
Got you.
Okay, well, this is us referring to myself saying Bitcoin was slow and this coffee thing or something related on screen. But okay, so here's this bottlenecks and scaling I was talking about. Should I go through this again, or it's fine?
It's alright if you go over it, maybe. Now that we can
Okay.
see it.
So computation load, like in Ethereum, it's gas. You're trying to execute some amount of computation per block, and the limit is the amount of computation you can shove in. And also, the other thing you have is like both state size and IO operations. So in Bitcoin, I think your state is the hundreds of gigabytes, and in Ethereum, it's well over 500 gigabytes. This is just this means that your full node has to have basically a hard drive dedicated to storing state. This is very expensive, and then you also spend a lot of time reading and writing to this state every single block. The third thing, which I think Drew was talking about, was like bandwidth or block size. You have a limited amount you can put in. This is imposed by your P2P architecture and your consensus time. So you need to reduce the amount you need to communicate. Consensus time, how long does it take to make a block? How long is finality? Data availability, this is not something that's talked about much. One problem you run into when making these, when having a blockchain is you need to make sure that everyone can see all the data. Or every full node can see the data. You could have in, say, Bitcoin's light client, you could be convinced that the chain is working completely correctly with no one, or with only the miners having the data. You could view selfish mining, in fact, as like a data availability attack. This comes up a ton in layer 2 sharding stuff, which I'm not going to talk about too much right now, but we can go into later. If you have any questions, please ask. Then another thing is light client assumptions. We can scale chains if we stop caring about assumptions, about security, right? So we want to do all this while keeping security good. And I'll argue this a bit later that the current light client security is not the best. Yeah, again, stop me for questions. Actually, can you see the full slide, or is it like blocked by Zoom's list of people?
No, I can see everything.
I can
Okay.
I can see everything. Yeah.
Cool. Yeah. So, any questions about any of these things?
Well, I have a question about finality. Isn't technically, like, Bitcoin is just technically never final, right?
Yeah. So we call this probabilistic finality. So the way you model this, you say, suppose you have an attacker has X% of the current computation power. After n blocks have happened, under some attack scenario, what is the probability that they can make a new fork n blocks deep?
Right. So as the number of confirmations goes up, the amount of compute you need to have been hiding secretly to then come up with a longer chain goes higher and higher.
Yes. Since everything's probabilistic, it's like a probability distribution thing.
Yeah. Can you explain a little bit about how Casper, I don't understand this very well, I just know it on the edges, but Casper FFG, how it solves that problem?
Sure. Okay. So forget Casper, because there's a great slide by Dahlia, who's a consensus researcher, which is essentially saying that take Tendermint, make it really slow. You have Casper. So Tendermint is the underlying thing, which is easier to explain.
Okay.
So you can imagine, I guess let me back up a step, and you have consensus, which is essentially a bunch of nodes agreeing to a thing. this is not unique to the blockchain world, in fact. Like, you have this in databases in Google. Like, suppose you're logged in to Google via your phone and your laptop, you're doing things with both of them. You need to make sure that both those edits are synced to the same account in Google's database. So Google has to run a consensus algorithm amongst all their databases.
Mm-hmm.
The problem with Google's consensus algorithm is it is not fault tolerant. Like, they trust their own servers. So in the blockchain context, we use a consensus algorithm among nodes, where we also want the property that if nodes are cheating or if like they're malicious, they can't edit the state. You need a certain proportion to be malicious in order to get an attack to succeed. This proportion is like 1/3. So we consider proof of stake to be secure, or like as long as 1/3 of the measured resource is not being malicious. So what these do is they're running a multi-round consensus algorithm among some restricted set of nodes, and then these nodes are either going to like these nodes are either going to agree or disagree, or like they're all going to agree that this is the current block state, or they're going to not come to consensus. So you're given essentially this, like, after a few rounds, since they agree, we're also now finalized. We have this proof that you've all agreed to it, or one of you is being malicious. Does that make sense?
Yeah, that makes sense. Thank you.
No problem. We can also talk about this more at the end. Like, it's actually a very interesting area. Okay, so these are bottlenecks of scaling. Now the title said SNARKs, so let's see. What do SNARKs change here? So computational load is basically eliminated. This less than 20 TPS should be removed. We fixed the TPS problem like on its own. For state size, we're going to improve IO to become like strictly minimal under some sense. And state size, we don't touch too much, but there's one other technique you can do, which then basically makes state size negligible, or not really a problem, that we can touch on later if people want. Bandwidth, we're also going to compress bandwidth. Consensus time is something that if you're not careful, we're actually going to worsen, because SNARKs take time to compute. So you have to design your system carefully that you'll count for this time overhead of the SNARK. If you're using proof of work, really, it's all fine. This matters much more when you're doing proof of stake. Data availability, we're not going to touch this. It's completely orthogonal. And then light clan assumptions are something we're going to fix with SNARKs as well. Okay, so first, what is a SNARK? A SNARK is a cryptographic proof that if you do some computation, the value is correct. So without SNARKs, you have some server and a client, and some function f, and like the server wants to give the client f of x, where both people know x. For some reason, the client wants this. I don't know. Maybe it's it could even be information. Whatever. It could be like maybe your smartwatch wants some data based off of like past health records. I don't know. Like maybe you want your average heartbeat or something for the last week, and you don't keep all your heartbeat data on your watch. Currently, the server just tells you the answer, and you just magically believe the server is correct. You trust them because they're some company or something, but you have no way of ever knowing they you have no reason to believe that they were correct. So a SNARK is using cryptography to fix this. So here's some example function just to ground things, like let h be a hash function. Suppose you want to hash some input 1,000,000 times. The input is x append with the secret. The prover knows the secret, the client doesn't. So in this diagram, you can see that the server is creating a proof of f(x) equals y. It hands the client a proof, the value y, and the client checks using the SNARK verifier that this proof validates the fact that f of x equals y. So this removes the trust in the server for checking what is that the server just didn't give you garbage, that the server actually gave you the correct value. And like this is huge for any sort of like securing yourself against attacks. If this data matters, you want to know it's correct, or if this computation matters. So this also, I wrote here like malicious companies, but another thing this is big for is like compliance. You may have heard in some, I don't know, industry use cases that companies being compliant with things matters. And so now adding this proof is a way for the company to convince you that they're being honest. Like currently, suppose you trust, or you want to trust Google, but you have no reason to. There's nothing really that Google can really do to convince you that they're doing the honest thing. Like they don't have a tool to like tell you mathematically. You just have to. You can't do better than taking their word for it. So SNARKs are giving you this property. Now, what is this word SNARK? I'll go to that in a second. So SNARK stands for zero knowledge. This is the like zk-SNARK or zkp you may hear sometimes. Zero knowledge means that the prover doesn't leak any data besides the input. So we earlier I was saying fx is like repeated hashing of x comma secret. This means that the prover could provably keep all data with the word secret hidden. So the client knows that this function involves secret was executed correctly, but learns nothing about the secret other than what the output told it. This is actually pretty big for many things. It gives you Zcash, which is a cryptocurrency where for the first time ever, actually, and it's still the only case where this is true, I can pay you, you post this on the blockchain, but the data on chain does not leak the amount or any data about who it's coming from or who it's going to. All other privacy coins leak a lot. This leaks the mathematical minimum. So this is sort of the point about if your phone's a prover, you can hide details. In Zcash's case, you can hide these transaction details. So the S in SNARK stands for succinct. This means that the proof I hand you is going to be very small and quick to verify. So for the previous function, the verifier time, maybe it took the prover hours to compute, months to just compute the answer. Then the verifier should be able to be convinced in milliseconds, like concretely 10 milliseconds-ish. So this is a huge gap. We want the proof to be non-interactive, so the prover just hands you a thing. You don't need an interactive exchange. And this also means that it can be put onto a blockchain. And you may start seeing a pattern where from this point onwards, we start selecting which words we want to capitalize and include in the acronym. So next is argument. An argument is like this, it's this thing in cryptography jargon where it means there's some probability of error. Like to do anything useful in cryptography, you have to accept some error rate. Otherwise, you run into complexity theory issues. So this means that like with probability 2 to the minus 128, it can fail. Like I can make a false proof. And then an argument of knowledge. So what knowledge means in this is the prover, if I don't have knowledge, if I just am a proof, that means that there exists a solution to this problem such that f of x equals y. But suppose, like for the example of f of x, that where f is repeated hashing of something, hashes are bijective. This means that there exists, or we believe that there exists an input such that, for every output, there exists an input that hashes to it. Like for every y, there should be some x such that h of x equals y. And this is not good enough. We want to know that the prover knows this x. Like think about for another example is for signatures. Suppose I want to prove that I know a signature, which is going to come up later. Then if I just gave you a snark that there exists a message that has a signature, well, this is not helpful. It's easy to show there's a message for every given that produces every given signature. We want to know that for my that I know that message because I don't have the private key. So the knowledge thing is very important, but I guess, yeah. Okay, so now how do we use this? Oh, sorry, let me back up. How efficient are these things? Are they useful? Well, the field for this is continuously improving. Like verifier times I mentioned earlier is like around 10 milliseconds. This is incredibly quick. You can even parallelize this verifier. The prover has some high overheads. So first you have to write your code in your function in this SNARK-friendly language. There's a few DSLs for this, like one that looks a lot like Rust. This is called Zinc. One that's like normal OCaml. It's called Snarky. Something that's equivalent to writing like logic circuits, like 16A, 16B style stuff. Sorry, no. Like 61C, the circuits you do in 61C, like of ands and nots. That's called Circom, and there's another custom language, Socrates. So you write in that language, it compiles into some math form, and once you're in that math form, the prover is around 1,000 to 5,000 times more expensive in that form. And this is one of the things that's improving all the time. And proof size depends on your trust assumption. So essentially, we have snarks that are trustless, but if you want to make a trust assumption that at some point in time, or there's a group of people such that at least one of them was on, or sorry, what will happen is you'll have a group of people come together and they'll try to produce something, some special value for you that is toxic. They'll try to produce some value for you, which a verifier can use to verify these snarks with smaller proof sizes. But if the process of making this special value for you requires that you trust that at least one person in this group was honest, that there was some randomness they forgot, which is very problematic in the blockchain setting. So if you have a trustless snark, we call these STARKs, your proof size is like 100, 200 kilobytes-ish. If you have a one-time trusted setup, or I shouldn't just write one time, I should also write like updatable. You can get proof sizes that are like 1 to 5 kilobytes. So by this, I mean that I can make some parameters, put them on chain or something. Then suppose you don't trust me, you don't trust anyone who's done it before, you can update these parameters. So you can, and since you trust yourself, you trust all snarks that use these. And then this repeats for everyone. Like anyone can keep on updating this. So this setting has pretty good proof sizes, 1 to 5 kilobytes. And then the current setting, which is what's been deployed so far, or the other two settings are about to be deployed, but the already deployed one, Gross 16, requires a new setup for every single algorithm that's going to be deployed. This is very problematic. But your proof sizes are tiny. Like to date, they're the smallest, and your prover is the fastest. It's just kind of cool. But these trustless snarks also have a couple other properties. One is they're post-quantum, and they require no like number theoretic assumptions. Okay.
What does post-quantum mean?
This means that suppose quantum computers exist, like that are big.
Yeah, okay, gotcha.
Then they can break like signatures, discrete logarithms, and stuff, but they will not break these STARKs. These STARKs only rely on hashing being secure, which is also what like encryption and Bitcoin also relies on,
right?
Which is known to be post-quantum.
Right. And then also, so about implementing SNARKs. So
Yep.
say you wanted to, say Bitcoin wanted to implement it, that would require a hard fork, right? And what do you think about like the feasibility of that sort of stuff?
It definitely would require a hard fork. And they were very opposed to these trust setups in the past. So when like Zcash existed, it still is a fork of the Bitcoin code base.
Right.
And they're trying to add these private transactions, or they added private transactions on top using SNARKs. Bitcoin said, no, we're not going to add this for two reasons. One is novel cryptography. And we're very conservative. We don't want to trust this, because if your cryptography is broken, then the money supply is like, people can print money if you implemented it wrong, or got some theory wrong. The second reason was they didn't like this trusted setup. The initial Zcash trusted setup was 6 people, and it was not an open set. It was like they couldn't add a 7th person because at that time the method of adding more people was like quadratic overhead with very big constants. It has since been improved to be like linear overhead and rounds and stuff. So it's very feasible. And the last setup was like open to the world and over 100 participants, if I recall correctly. So, but I think if Bitcoin's going to adopt a thing, it's going to be like SNARKs. Because they introduces no new assumptions, and they already trust hashes, and has no setup.
Nice. All right, thanks.
No problem.
Hey, Dev, can you talk about the computational time for generating these proofs?
Yeah. So, okay, you have high overheads, but they're also not like infeasible, and they're completely parallelizable. So your prover could be on a GPU and GPU the whole thing. Are people here familiar with finite field arithmetic? Or like, if not, I won't go into it, but if you are, I can add some more details. Okay, no takers. All right. So your prover, you express your computation in this other form, which involves like matrices and vectors, which is what your front-end language is going to handle for you. Like when you're writing code, you're going to write in something normal looking, but then it's going to compile down into this mathematical form. And in that form, the prover takes like 1,000x overhead to 5,000x overhead. And to ground this a bit, I'll try to think of some numbers off the top of my head. Like, so it turns out that hashing normal things is very hard. So doing like a hash of like a SHA-2 hash adds like seconds to your proof generation time, maybe like 10 seconds or something, and for these SNARKs, something in that ballpark. And this, so doing a Merkle tree path verification is like around a minute. So you have to use parallelization for this, but it turns out there's this line of work called SNARK-friendly hashes that mitigate this cost. Then I guess additions and like are really cheap. Arithmetic is cheap. If you guys have heard of Monero, they've deployed a SNARK for a limited use case. There's a SNARK that's really good for what's called a range proof, proving that a number is between 0 and some other number. Like, I don't know. And in their case, I think it's like proving numbers between 0 and 2 to the 32 in zero knowledge. And they use a SNARK bulletproofs to do this. And this gives them the best concrete, like the minimal proof size for their ring signatures. And the proving time for that's like less than a second. I don't know, does this answer, or do you want like some more details about time? Is there any specific question you have?
Yeah, sure. How would you usually parallelize it, and what are some of the methods people use to do that?
Oh, sure. So all the things you're doing are fundamentally parallelizable in a SNARK. There's maybe 3 sort of bottlenecks you do. One is FFTs. FFTs are known to parallelize. It's actually a bit complicated how they parallelize. In CPU, they parallelize up to like a certain factor very well. I don't know, maybe like 16 or 32 something. And then beyond that, you run into like caching issues, which are hard to deal with. And this stays the same in the GPU level. But when you go to an ASIC, you can fix these caching issues. Are people here like into the ASIC side of things? If so, I can go into that in more detail, but okay, sounds like no takers. The second thing that these SNARKs do is sort of trivially parallelizable tasks, like a linear combination, like a1.b1 plus a2.b2, et cetera, et cetera. This is trivial to parallelize into n chunks for whatever n you choose. You just like, vectorize it and have process 1 do the first set, process 2 do the second set, et cetera, et cetera. So easy to parallelize. The third thing is linear operations on evaluations. Like suppose you have a vector A and a vector B, A plus B, constant times A. Again, very easy to parallelize. So these are actually even map reducible. Does that help?
Yeah. Yeah. Thanks a lot. Yeah.
Okay, no problem. Okay, now this is enough about what are SNARKs. Let's look at a case of what they can do. So first, let's look at what happens in a blockchain without consensus. So you have a block producer. The block producer is going to sort of collate the transactions together and commit to them and like via consensus. They're also going to give you a new block header and like Merkle tree state root. Like this is a commit to the new blockchain state. Then, this is the block format transaction set of transactions are committing to in the new root. You're going to give this to every full node, the P2P network. That parts are important. And they every full node has to re-execute every transaction, and they check that they got the same state root as the block producer. And this is what makes the fundamental like computational overhead that I was mentioning earlier. Since a single transaction has to be executed among every node, that means that your chain has to be parameterized for the slowest full node you want to support. So like if you had n full nodes, t transactions, you had to execute a transaction t times n time, or the total number of transaction executions is t times n. So this is literally the opposite of scaling. To scale something, you want to do less work and parallelize it. Here, we're duplicating it. We're duplicating one job n times. And so this means that your block producer can't use parallelism, GPUs, faster algorithms, et cetera, than the full nodes. They have to be doing the same exact work at a slow pace, and we can't pack more computation into a block. But with the SNARK, we can fix this problem. So first, a block producer was going to gather transactions, execute them, and figure out what state has changed. It then makes a proof for this. Okay. So the block looks like state changes, new Merkle tree root, and a proof. It gives this to every full node. Every full node verifies the proof and applies the state changes. Okay, so question for you. What is this algorithm that is being proven? Like I said a proof, I didn't say what exactly I'm proving. Any sort of guesses or at this?
You're just proving that those state changes result in that new root.
That is one part of the algorithm, but it's not good enough to just know that there exists some state changes. Like, what if my state change is spend all accounts that are send all their money to this address? Like, yes, this is a state change that could happen, but should it? Like, is that a sufficient proof? Or here, how about this? Like, I'm the block producer. I collate no transactions in the rest of the world, but I say like, Simon, all money in Simon's Bitcoin address goes to my address. So do you see the problem, or you're really close?
No, I'm confused. I just thought that if the state changes and producing a certain new root is verifiable using the proof, then if you change the state changes, then you're going to get a different root, and the proof will fail. But
so that is correct. That is completely correct. The part that is, it's just mildly insufficient. The problem is you also need to know that every state change is authenticated.
right.
So that like, if I'm trying to move Simon's money to my account, Simon needs to have made a transaction with a signature on it.
But you can verify that using
Yes.
the signature itself, right? Yeah.
Yes, you can verify the signature, and then this is algorithm sufficient.
Right.
So yeah, and I guess to recap, the algorithm that we're verifying is that every state change is authenticated by the correct accounts, or like, signatures, whatever your state machine says. Like all computation is, then all computation follows the code. Like, if we're doing Ethereum EVM style stuff, we need to know the correct algorithm is being specified for executing the VM. And then we need to check that all these state changes that are listed change the proof, or like, sorry, give us this new Merkle tree root. So now something interesting is full nodes are doing like minimal IO work. So I'm literally giving them the state changes, and then they just check that they update. The IO they do is changing those state changes. They have no extra reads. Like, they don't need to, yeah, I guess, or minimal in the sense. Like, suppose there's some transient global constants or global variables. They don't need to check that in themselves. They just have to check that the prover is going to check that. The prover will say that this public key, or the correct public key signed off on this account, and because the Merkle tree root is already correct, this update is correct. Then the block producer now can put as much computation as they want. The block producer could be the world's fastest supercomputer, and everyone can still verify the proof, because the verification time, or the work of a full node, is independent of, or roughly independent, it's logarithmic, in the amount of work or computation packed into a block. It's like 10 milliseconds.
But Deb, so I have a question. Okay, so it sounds like the computational load of verification gets offloaded onto the producer in terms of producing this proof. And so instead of doing something many, many times, you can do it just once. Exactly. But that kind of reduces how democratic the blockchain is, because now you just need more compute resources to be an efficient producer, right?
Yes and no. So we always had some sort of consensus algorithm. So okay, let's go over the two consensus algorithms. Like, so in proof of work, you needed ASICs anyway. Like, you weren't going to compete otherwise. So we didn't really we didn't undemocratize it. We said, like, because having high computation is part of it. And suppose you didn't have a large computer, you would then just include fewer transactions. Like, you would include as much as you can within consensus time, and then you would this would be a smaller number, and so you would get less fees. So it's sort of, you're being rewarded, of course, in an amount that's complementary to the amount of work you do. But then the claim might be that, okay, I was comparing proof of work, and in proof of work, we already assumed tons of computation power, but what a proof of stake? In proof of stake, we say that it's just two modes of proof of stake, I guess. One is Tenormint style stuff, like Casper FMG as well, where you have a limited validator set. Mm-hmm. And in that setting, in some sense we have limited, in some sense we haven't. So technically anyone can still be a validator, in the sense that, like, if you have enough stake, you could be there. And you could, like, make blocks that are just happier transactions than your opponents, or like your other competing validators. Mm-hmm. And so you get less fees. And this means that no one's going to delegate to you. And so in this sense, you do lose out, because since you have less rewards, why would anyone delegate to you? No one will. And so you don't get included in the validator set. And this is a state of the world, but I think it's an okay trade-off, because the model is never everyone with a laptop is going to be a participant in consensus in this, because then they have to be always online. There are some people who disagree, namely the Avalanche community, and they have an interesting alternate proposal, but they don't solve this computational problem.
Okay, thank you.
The second model consensus, I guess, is Avalanche and Ouroboros, and they say that okay, we'll just not let computation scale, and I think this is a trade-off you have to make at that point.
Okay.
Yeah, good question. Great question. Great question, actually. Okay, so now where do we stand in terms of like how SNARKs improved our blockchain? Well, in terms of computational load, we packed in as much as the miner did. For state size, we've done nothing, like literally nothing. For IO, it's now been minimal. For bandwidth, we communicated just the state changes, not witness data. So we did not include transaction signatures, and so now you can just compress state changes in the minimal manner, like in whatever way minimizes that. For instance, like if you know that these three state changes always happen together and can be described with this smaller description, you do that. So this is a very notable improvement there. Like in fact, where the improvement between just do people see like why does a transaction encodes state changes plus more stuff like signatures. So now we've removed everything but the state changes. And in a lot of applications, this is a massive improvement. Like Augur is this, I'd say it's a, Augur, or actually no, I'll keep going Augur. It's a prediction market. So you have lots of changes where you really only need to store the most of it's like aggregates of data. Or if you have a side channel, like suppose I pay you and then you pay someone else, we can remove the same amount. We can remove the intermediate step of your balance changing. So this removing state changes helps a lot. For consensus time, it depends on how you do things. You can do things such that you keep the same consensus time, but if you're not careful, then you can actually like worsen consensus time, or depends on how you want to structure the guarantees. And so at best, it does nothing for consensus time. At worst, and really most cases, it's probably going to slow down consensus. For data availability, this is completely orthogonal. Like, yeah, it's not related. And then we're talking about like-kind assumptions next. Any questions about this stuff, or?
Yeah, I've one like kind of broad thing. It almost
Only
like,
one.
yeah, you know, like it almost feels like it's like magic, almost like you can like condense this all into like a proof, which does take a lot of time, but then once you send it out, it only takes like a small time to verify. So like almost in like not going into too deep, but like what are like the cryptographic like innovations that might have made this happen or like possible? Or like what
Yeah.
like people were like, yeah, I can do this. Yeah.
It is kind of magic. It's really exciting. So I guess a thing to note is that this didn't come out of nowhere. This sort of area of research started 30 years ago and just started becoming practical in 2015, 2014.
Right.
So we've now distilled it down to maybe like 2 steps or 2 parts. One is an information theoretic part, and one is a compiler. So the information theoretic part is going to say that your problem is satisfied as long as there are these polynomials are of certain degree, like degree d, not d plus 1. If it's d plus 1, it's invalid. If it's d or less, your problem is satisfied.
Okay.
And then we combine it with the polynomial commitment, which will say that, which is cryptography, to say that yes, this is a commit to a polynomial of degree d, and you can open it at certain points, and then you're going to check that some properties hold between these polynomials.
Gotcha.
I guess maybe another high-level explanation is because that doesn't seem super convincing. Maybe like, suppose this following thing exists. What's called a PCP, or probabilistically checkable proof. That I'm the prover, and I'm going to make a very long string thing, and then you're a verifier, and you can see that if you check my string at just a couple points, and some mathematical relation holds, this is equivalent to the problem being satisfied.
Got you.
Yeah, I guess it's a bit hard to go into like much more detail without like more math, but we can maybe try it at the end.
that makes sense. The kind of reminds me of like stuff I might have learned in like 70 and stuff.
Yeah, so a lot of it's all using error correction codes underneath.
Yeah, that kind of stuff. Yeah.
So you somehow make a function-based error correction code where like, or you make multiple codes, and then if they have certain algebraic properties between them, it is like satisfied, and you get properties with the entire computation because it's error correcting.
Okay, that makes sense. Thanks.
No problem. Okay, so now we're talking about light clients. Are people familiar with light clients much? We talked about it in the DeCal before.
I don't think we talked much about it.
Okay, exciting. Then you guys all get to learn about light clients today, and then learn why how we improve them with SNARKs. Okay. Oh, sad. This isn't. So right before I was about to talk. Keynote crashed, and so I redid the animations for the first few slides. I guess it didn't get here, so it's unanimated. Sorry. A light client's a small computationally restricted node, like a phone or IoT device, or in the initial comic, which I guess didn't get really seen because of zoom errors. It can be a cafe shop register. And they want to track the blockchain because you want to be paid on this, or you want to make payments. So how do you do this? The method we do is the light client. Because essentially, your phone can't have the hundreds of gigabytes of state. It can't rerun every block. Blocks take maybe it takes a couple seconds to run on a computer. On your phone, the block probably translates to 10 or 15 seconds, which could be then bigger than your block time. Therefore, you never sync up, et cetera, et cetera. So what a light client does is it's going to track consensus. It's going to verify that consensus has approved of this following state root. So in Bitcoin, this might mean, or proof of work means maybe it follows like the latest 10 state roots because of probabilistic finality issues. So they receive every block header, and then they check that consensus between the previous block header and this block header is valid. And then you just at some point you forget about the old headers that you don't care about, and you just magically trust that the state is valid. That the transition between two headers is the state computed is correct. Suppose because the light client has no idea that if their money's been drained, or if the miners stole money from Simon and the light client is not Simon, then you don't know that this happened. You don't know, which would be very problematic, especially if you're doing Ethereum style general computations. So just to give some insight, this is very bad. First, the not trusting state. Maybe you can make some crypto economic guarantees, but it can take so maybe that's not the worst. Depends on your belief set. I think, but it is really problematic to get all block headers. This is literal gigabytes. So this is prohibitive for smartphones or something. It takes tons of bandwidth and could be days of computation. So in Bitcoin, it's unlikely it'll take you a full day, or on a phone, it'll take you a full day. Maybe it'll take you 12 or something hours and a lot of your phone's battery. But Ethereum, it certainly will. I guess if people are into low-level stuff, I can explain this a bit more. But due to block hash stuff, and Ethereum block hash is very slow on embedded devices. Plus, you just have hundreds of thousands of these that you have to go through. So the current state of being a light client means you have to just trust a ton. You can't even verify the consensus got you from Genesis to here. You can probably just verify that here is some full node I trust completely, and here's what they're telling me, which is not a great situation. So the whole point is we want provable security properties. So SNARKs let us sort of retain this provable security property feature we wanted. So let's look at a light client with SNARKs. What you do is you receive the latest block header and a proof that this block, this block header, the latest block that this block header represents, and all prior blocks until genesis are valid. So the proof attached to every block convinces you the entire chain is valid. Valid means that like not only was consensus valid, like the proof of work case, but all transactions were executed correctly. Therefore, state is valid. Just like what we did with scaling. And so this solves your syncing time and data size, because now you just need the latest block header. That's all you, and the proof. That's all you need to sync. And now you don't have to trust your full node to either save you those days of bandwidth or just for computing state. You get that automatically. So there is a blockchain that's building this out. It's called Coda. And here's like some numbers. So ignore the staking node line, or maybe we can talk about it later. They're using a second trick called stateless verification. But their light clients, the user nodes, are 22 kilobytes, not gigabytes. And they sync basically instantly, in seconds. So this is like what using a SNARK lets you do. Does it make sense what's happening here? Okay, I hope silence means a yes. I know it's not always true. So
Yeah, it makes sense.
Cool. There's a subtle problem with what I said earlier. About, does anyone see a subtle problem with like the light client getting a proof that the current block is valid and it is an execution and all prior blocks in history are valid? It's kind of a subtle problem. It's not obvious. Don't worry. Okay, so the problem is that the amount of computation, like I can't just make a proof about all of history. Suppose there's been n blocks, each of size t, then my proof is like proving time on a statement of size nt, which can be prohibitive. If we pack enough computations in each block such that t is like minutes, that are parallelized minutes, but still minutes, and n is like 1,000,000, that'd mean that doing a proof would take days. So we can't do that every single block. That's way too expensive. So what we do is introduce a new trick called SNARK recursion. In principle, this is not hard. Like, in principle, I want to do a SNARK that here's a proof that block 0 to block n-1 are valid. Now I want to give you a proof that n-1 to n is valid and check that all prior proofs are valid. In principle, it sounds easy. In practice, this actually has some complications. So here I'll go through what is recursion like for an iterated function application, which is actually the blockchain case. The blockchain case is verifying a block and transaction execution as your function. You execute every single block. So let your function be f. First, and your input like be z0. So first you prove that f of z0 equals z1. Then you prove that f of z1 equals z2. And that basically the proof for f of z0 equaling z1 is valid. And then the next time you prove that the function of z2 equals z3, and that the proof for z2 is valid. And note that checking the proof for z2 implied that z1 was valid as well, because the proof for z2 encoded that fact. Does this make sense? Should I go over that again?
It makes sense.
Okay, cool. So this is a really powerful property, because now this means that let like z1 be block n-1. That's our proof from genesis to n-1. Now the proof for the nth block is cheap. It's the execution of block n plus verification of block n-1. Since verification is small, 10 milliseconds, this whole thing is very small. So another important property for blockchains is that using recursion, you don't need the same prover to prove every single step. Like, And this corresponds to having different minors. Like, so miner 1 produced block n minus 2. Second miner produced block n minus 1. You produced block n. And you just needed the prior proof to do so. You don't need anything else. So this lets you use succinct blockchains. That's the name of what Coda is doing, or the succinct light client thing, because it also gives you important properties for your full nodes as well. It enables something called verifiable delay functions. I don't know if you talked about this in class. If you have, this gives you like post-quantum continuous verifiable delay functions. And it's the actually only way that is known to get both those properties. It gives you SNARKs for map reducible functions. So it's interesting that you can model a lot of things. I guess a lot of things are map reducible, as you're familiar with, and this lets you do it efficiently. And another thing is you can have like an internet with a lot of your computer results being authenticated with recursion. Like, someone commits to some data set, you do some analysis in the data set. Like, here's this coronavirus deaths by country as stated by who or somebody. Then you make a blog post and you can prove that the numbers you made up weren't exaggerated or hyperbole or like out of your head. They're actually from who numbers as of some date. This has been, I don't know, at least if you follow Twitter as much as I'm fortunate to be doing, I think it seems like it's been a problem with people spreading some lies about some things. This lets you fix that. And more. Okay, thanks for your time. Please ask questions about any of this, anything related to SNARKs or blockchain scaling.
So I may have missed this because your voice is cutting out, but the recursive proofs, are they small enough to do on like IoT devices or smartphones? Or is that still limited to like larger computers?
Smartphones, yes. Like this is being done. This is what Coda is doing. IoT devices, I'd have to think about this for a bit. Like, it depends on how live your IoT device needs to be. So the smallest we can get these proofs to be is maybe, off the top of my head, maybe like 5 kilobytes, really. Yeah, and that's just huge overheads. And I don't know if that's small enough for IoT devices with their other overheads.
Okay.
On the
Dave,
proof
could you
size.
put- oh, sorry, go
Sorry, I
ahead.
didn't hear that.
You could go ahead. Sorry.
Oh, on the proof size front for like transparent things, like fully trustless mode, these could be better. The initial results seem like these could be better for IoT devices. The current proof sizes are 100, 200 kilobytes. Those will probably improve, but for other things, it's not clear. Yes, we may you may need bigger IoT devices to do so.
Yeah, this all makes sense kind of conceptually with like, large level building blocks of like, oh, this magical proof thing. But do you have any recommendations on reading we can do to understand like simpler, low level?
Yeah, how you build these things?
Yeah.
Okay, there's 3 things. I can probably send it to Minxing to send you via email. There's a blog post series by Vitalik and another one by Zcash, which do a good job. There's a talk by Alessandro Chiesa that explains in better depth, like, what are the building blocks you compose to build some of these SNARKs. And there's actually a work like by Cornell, like that came out 2 months ago, I think, which is supposed to be the simplest SNARK that you can just understand as a standalone object.
That would be awesome if you could send that to Minxing.
Yeah.
Or is it possible to just send it now?
This I could try. This depends on my online Googling skills.
Yeah, or maybe just send it to us, and I'll post on the website.
Okay, perfect. That sounds better.
Yeah.
Thanks, Simon.
Yeah, I mean, it's a bit too much math to go into like without a good whiteboarding solution, and probably requires like sitting with it for several hours.
And Dave, just a random casual question. What's like your wildest dream zk-SNARK application that you might have in mind? Something that you're like, could they be used here? Or it'd be really cool if it could like be used here. Do you have any like current thoughts?
Huh. So one thing that is really cool, I think, is a web with everything authenticated. Like all computed results could be proven. That's, I don't know, I think that's pretty exciting. There are also privacy use cases. One is, I think Zcash is the most interesting use case of blockchains. Zcash is the thing I was looking to with that you can use zero knowledge for. I didn't spend too much time on zero knowledge, but essentially you can use it to make a currency where I can pay you. We have a blockchain import, and no one knows who's coming from, who it's going to, or how much is in it. You can use the same zero knowledge property to do a lot more things. Like, all these phones really want you to have ML. This is unfortunate.
Sure.
And you don't know that these companies aren't like sort of stealing your data and stuff. So at least something they could do is, or actually, suppose you want the company to classify something for you. You don't even know that they classified it for you correctly. Like that it wasn't just a human or some massive bias. So you can use these proofs to like ensure that your model is being computed correctly, and you can hide your model. But more interestingly, on the data side, you can require that in this federated learning model, they aggregate your data correctly. This doesn't really solve all the problems. There's lots of problems with federated learning, but it helps mitigate some of it at least.
Cool. Yeah, thanks.
There's some work with using like private peering networks where suppose we have some relationship graph where I know some of you, you know other people, etc. We want to make a connection or like send payments between two of us. We could do this while also hiding who every single participant knows using like zero knowledge recursion.
Nice, that's cool. And then I saw like on one last slide that like when you like went to the very last slide, you talked about like interoperability with SNARKs. That seems pretty cool. How does SNARKs like kind of tie into that?
Okay, so first, blockchain interoperability. We have several independent blockchains. We want them to communicate. And so, like, first let me start back. Why do we want independent blockchains? Well, blockchains are like a monetary policy is kind of like having a nation state. And monetary policy is perhaps one of the most key questions for will blockchains work in a decentralized manner. So we want many different monetary policy experiments. This requires independent blockchains because monetary policy has to be tied to consensus in some aspect. So, okay, multiple blockchains, and currently they're all siloed. Bitcoin can't communicate to Ethereum, can't communicate to Tezos. So we want them to be able to transfer assets across one another.
Mm-hmm.
And so a protocol to do this, you can use light client proofs to do this with atomic swap and stuff if like both chains comply with this protocol. This is what it's called. There's people working this. It's called IBC, inter-blockchain communication.
Right.
And this requires where each chain just trusts consensus of the other chain. So if one chain has a consensus fault and double spends or steals money from this, it can cause failures.
Yeah, that's bad. Yeah.
So IBC limits this to that it only causes failures for things that came from that chain, but it's still bad. And so SNARKs eliminate this sort of computational fault or fear of that.
Oh, nice.
Then at worst, you have like forking risks, and that's actually easier to handle at this level, like at this macro chain level.
Right, that makes sense.
Because it's hard to eclipse an entire chain. This means that you have to eclipse every single full node who uses that chain. Yes. Assuming some subset touches both chains, then it's very hard. But it's much easier to eclipse you and then double sign or like give you a different fork.
So like in these faults, so like normally with like normal interoperability solutions, like they might be like if there's a fault in consensus, they're like, oh well. But then like with SNARKs, it's like their way of going around is like creating a fork or like and then fork like resolution. Is that like what it's like or?
First, I love that you said normal interoperability solutions. This just
Yeah.
makes me feel happy considering none has been deployed. But we can already start calling obviously normal.
Right.
So yeah, what happens is by consensus fault, I assume there's two things you can mean. One is you
Okay.
mean that there's two different commitments that are competing,
Hmm.
and only one should exist. But, like there's a fork, basically.
Yeah.
Second is that you mean that there has been, you committed to an invalid thing. You've committed to incorrect state. You didn't, some transactions invalid that you accepted, et cetera, et cetera.
Cool. Yeah, I'm thinking about like the double spend case or something like
Okay,
that.
so the double spend case doesn't change between SNARKs and not SNARKs. That's a consensus fault.
Okay. And yeah,
But-
what happens for that.
Yeah, but at the macro chain level, this is like not a big fear. You basically just allow some, I don't know, a couple seconds for someone to report a secondary block, or you optimistically assume it's not going to be a problem,
Mhm.
and it's resolved. But then at the incorrect computation level, it's a huge concern. Like suppose you have one chain that's supposed to give randomness to the whole world.
Right.
Because I guess getting on-chain randomness is hard.
Yeah.
Then you have to then you want just one chain doing it, so at least you can centralize the hardness to just one area. And some solutions you actually have hardware requirements. So then you isolate the hardware requirements, just one group of people, and everyone can then get secure randomness from that. Well, if they cheated on, if someone computed incorrect randomness and then just said, yeah, this is the incorrect thing, and you believed it, this could mean that your lottery is invalid.
Yeah, that's bad.
Yeah, or if you're using randomness for consensus, which I think most things should, then you have even bigger failures. So in this setting, you really needed the computational validity, which is what
okay,
SNARKs gave.
and that's what SNARKs get. Cool.
Yeah.
Nice. Okay, thank you.
Problem.
Yeah, Dev, I have a question.
Yeah, go for it.
Yeah. So SNARK sounds so wonderful with this, all these kind of advantages over the current solutions. What do you think is the major roadblock that's blocking the adoption of SNARK?
There's a couple. One is the provers are slow. 1,000 to 5,000 is a very big number, and this is on top of the problems of translating it into the language. So something I should have raised some big flags is SHA-2 taking seconds to something on the order of seconds to prove one execution of. SHA-2 runs in nanoseconds, under 10 nanoseconds on your computer, and often you count it literally in cycles because you have hardware acceleration. It taking on the order of seconds scale means that there's huge overheads before the 1,000, 5,000. Because, nanoseconds to seconds, that's 10 to the 9. It turns out that that example is because SHA-2 is particularly bad for SNARKs. SHA-2 is optimized for using lots of bitwise functions and bit shifts and stuff, which don't translate into a SNARK at all. Then you have the SNARK overheads and vectorize things. And SHA-2 uses vectorized things which don't translate well. So you have different optimization targets. For hashing, at least, there's new work on improving hashes that are both secure and for SNARK, good for SNARKs. And so I guess to answer the question, it's one of the problems is this huge computational overhead. I don't want to paint a picture that's 10 to the 9 times worse. This is not true. It's often 10 to the 5 or 10 to the 6 times worse than native computation, which is big numbers. Then another problem is you need chains to be accepting of SNARKs. This is all novel crypto, and the SNARK algorithm keeps on changing because we keep on doing research improvements. So currently, Ethereum is the only chain besides Zcash that supports SNARKs in some capacity and is deployed. And Ethereum only supports SNARKs on one type of elliptic curve. And sorry, back up. A lot of SNARKs require special elliptic curves. If I go back to the diagram, it's the trusted setup SNARKs and updatable setup SNARKs. SNARKs, like the trustless stuff, operate over almost any finite field. Or like finite fields are numbers mod a prime. And so you need your chain to support numbers mod a prime efficiently or elliptic curves efficiently. And most chains just don't. They only support their native, like 1 or none. So there's a bunch of chains now that are launching that are going to support more things, which would hopefully allow for more iteration on chain. And the third bottleneck is just trust assumptions that these are hard to orchestrate in practice. There's actually a great podcast from the Zcash folks about how hard their first trust setup was and like how they had a potentially compromised participant because their laptop was hacked. Hopefully that answers the question.
Yeah, great. Thank you.
So if people want to talk about more about blockchain scalability, there's like a bunch of things we could talk about. I've worked on consensus, interoperability, and a lot of these things. Like we talk about layer 2, also data availability. I was a bit surprised no one asked any questions on it. Maybe it's because I skimmed over it very quickly.
Yeah, maybe elaborate a little bit on data availability because we haven't covered that in class yet.
Okay, it's actually, yes, attack this or a scalability concern that's really not talked about often. So suppose you have consensus and you're a light client. You want to also believe that the chain is decentralized to some extent. And this means that you may want to, that anyone, in proof of work, this means that anyone should want to build off it. Like it should not just be one single miner. Because you can sort of keep on changing your who's mining this, you want to make sure it's not just one miner. So if I'm a miner, what I can do is selfish miner, where I don't tell anyone else the block I'm making. I just give everyone else the block header and the new and the proof of work on it. You accept that, and then but then you can't mine a new block because you don't have the block data. But I start mining on that block that's been sort of pseudo committed to light clients. And this like causes problems. It means the chain centralized, et cetera, et cetera. But at L1, this is not a huge issue because you have a market or you have like competing validated miners. And in proof of stake, your consensus algorithm is actually a proof of data availability among the validator set. So in proof of stake, the equivalent problem is that all your validators are cluing, and only they can produce blocks and see data and make inclusion proofs, et cetera, et cetera. So they could be double signing and you accept. And none of the full nodes, all the full nodes are kept in isolation. But again, this is like not huge because if none of the full nodes get the data, then those like riot and they won't provide anything to light clients and no one gets things hauled. This problem comes up a ton when you're trying to do things like sharding or layer 2. So one of the proposals to scale blockchains is you shard. You sort of have like several parallel blockchains that we umbrella into one blockchain. Like they all operate over the same state tree. And so in that setting, in the sharded setting, you have to make sure the data for every block is available to everyone in one shard, is available to all other shards. Otherwise, state updates couldn't be applied. And we'd have huge state inconsistencies. In layer 2, like when you have a roll-up sidechain or a plasma sidechain, you need to be sure that the block data is valid. Otherwise, the block data is available. Otherwise, there can only be a single miner. Or you get similar cascading faults when multiple people are trying to operate over the same data. Like you couldn't convince light clients you can't make an inclusion proof to the latest state.
So would you say that there's more restrictions with layer 2 versus layer 1?
Depends. Like well, I guess factually yes, because layer 2 has to depend on layer 1. So in that sense, it certainly does. But this data availability problem happens when you try to scale layer 1 via sharding as well.
Okay.
So there is a solution to data availability. Oh, sorry. I guess it also matters on the Cosmos model, where you have tons of different blockchains for different tasks. And then if you are trying to do like inter-blockchain communication, you want some data availability guarantees to other chains. And as a light client, this is like also like a big light client concern. So there's this thing called data availability proofs, where I can prove to you this data was made available at some point in time. What this looks like is I take a block's data and I erasure code it. So in CS70, you guys probably talked about Reed-Solomon codes, where I interpolate the data into a polynomial. Well, and then I suppose there's, I don't know, the data corresponds to D field elements. Then I get a degree D polynomial, and I evaluate it over many points. I don't know, say 128D. Then any subset of size D is sufficient to recover. Is that? Yeah. To like recover the data, and you get some erasure and error guarantees, etc. Wait, I don't think I got this right. Okay, whatever. We use erasure codes, and essentially then, I think I got the amount you need to recover incorrectly, but you need some amount to recover, and you get guarantees over the entire data then. So what I'll do is I'll give every different light client a different subset of the data, a different like shard. And then if you're worried about data availability, you collect enough of these shards to convince yourself that the whole block is valid. So like as long as you see enough Reed-Solomon shard, like error correction chunks from different people, you're convinced the entire block is valid, like all the data is available. Does that make sense? Because like the data could be interpolated from these, and the chunks are consistent.
Yeah.
Okay, and you're using erasure code properties to argue consistency.
Mm-hmm.
Because they're fault tolerant, you then know that they'll. Okay, now actually, sorry. Now I remember what you do. So suppose you have like again, I guess, degree D thing, and you commit to 128D points. This means you have a rate of 1/128th, which means that you can tolerate up to 1/256% having errors. Okay, let me pick better numbers. Suppose I commit to 200D points. That means my rate's 1/200, and I can tolerate up to 1% having errors. This means that like if 1% of the points are if I know that like 1.1% are consistent, then the whole thing is consistent. Wait, no. Whatever. Okay, I can look this offline and get better details. I don't know. Sorry, on a presentation, I'm having trouble remembering this correctly. But the high-level idea is using error correction to argue that enough light clients have enough data that it can be recovered, and because the data is available, because light clients could recover it. And it turns out that these proofs are sublinear. They're like square root n. So like the amount of data I need to receive to be convinced that n bytes are available is square root n. So what I'll do is I'll bundle many blockchains data together. It's like what Lazy Ledger is. And they will make a data availability proof. Like they'll have a large set of nodes trying to do data availability for all of these chains. And so then because square root n is sublinear, the total data availability proof size is sublinear, and we have a much larger node set. So the size of every data availability proof also goes down with the number of different peers doing stuff. So by making a single chain that argues data availability for everyone, we both increase the number of peers, which lowers data availability proof size, and we increase the size n, which due to sublinearity improves overall bandwidth for the world. So there's probably a lot of information without correct scaffolding. My bad. I don't know. Do people have questions about like anything else like scalability related or SNARKs? If not, then I guess we could end earlier. I don't know. I don't really have a discussion planned.
Yeah, what would your favorite SNARK use case be?
I
personally?
think maybe there's two. I think the succinct block. I think blockchains along with privacy is a huge deal. So I think SNARKs are how you scale a blockchain, like are one of the fundamental parameters of how you scale a blockchain in like succinct blockchain style stuff. And Zcash privacy on top is a huge improvement over the current state of finance. The second thing that I think is really cool with SNARKs is you can get a fundamentally more verifiable internet. Like you could check any computed result. I guess I gave the example earlier about something coronavirus related. Like you can check that all these statistics are computed correctly. You could check that, like your browser could just check this for you. It'll say that here's some data set committed to by entity. Yeah, and then here's a proof, like it's given in the data. You don't actually literally see the proof. Your browser plugin checks it. That yes, and this is the computed value. Like I don't know, this is the average of the data set, etc. This is, I think, really powerful. Another thing is like it comes with photo editing. Like here's some original photo, like taken by a camera, and then here's a proof that it's only been edited by an allowed set of operations. If you apply this like across the macro level of the entire internet, I think this is an exciting thing where all things are provable.
Interesting. So by set of operations in a photo, you mean like sharpening, brightness, etc.?
Yeah, exactly. Like I don't know. I don't want a photo of me holding a water bottle and then this, I don't know, suddenly replaced with something embarrassing. I don't know.
Yeah, true.
Like a gun. Like that would be, I don't know. That would be an unfortunate case in a
Yep.
court case, an unfortunate piece of evidence.
Oh yeah, definitely. And so basically SNARKs could prove that if someone was trying to frame you for being a murderer with a gun, then it could prove that the photo was edited.
Yeah, exactly. So you need to do that, you need two components. You need a small root of trust in your phone. You need like a hidden private key, like an HSM, which an HSM says that there's a private key that can sign things, but you cannot exfiltrate the private key. So then when you take a photo, the private key will sign the photo's raw bytes. And then when you photo edit, you then just say that here's this initial signature on a photo and a set of operations were applied. Maybe you don't even know the set. Maybe it's zero knowledge. But you just know it's all operations are in that set. Hue, saturations, sharpens, et cetera, et cetera. Yeah.
And once you edit a photo, its private key or ID just becomes changed by the system.
You maintain an initial signature on the message that's like to say the same. Like I give you signature, proof, and final photo, and your algorithm says that there is a chain of operations that are in the set of valid things that were all applied, and the initial thing had the signature on it.
Okay.
Had the signature that's authenticated by entity, by HSM issuer.
Cool.
So I guess it's a bit closer to an SGX than HSM, because an HSM you set the private key and then no one else can steal it. Whereas here it's really like some company setting the private key. Well, actually, no, maybe it is more like HSM. SGX is a generic computation. There's some things I've heard about that I haven't really followed, but how it matters for companies like doing compliance work, where like there's some laws you have to prove that they're abiding, like data privacy laws or something. You can't prove you deleted something, but you could prove that your model at least only was trained on valid data.
Yeah.
So people are looking into stuff like that. Oh, I guess something I didn't talk about at all was why it matters so much in blockchain. And besides consensus, I normally think about consensus a lot, or like the base L1 scalability, but it matters a lot if you're writing an application. Because well, suppose you're writing CryptoKitties, not CryptoKitties, that's a bad example. Suppose you're writing like a DEX. A lot of your transactions, like you want L1 for finality. Sorry, let me back up. Layer 1 is a great finality engine. Like essentially you're paying a bunch of people to either be a proof of work or be a proof of stake to finalize data and like be a intolerant log or depend-only log. But the amount of data you put on there is expensive. You have to pay for every byte. So if you're an application developer, you would like to just continuously like, you don't want to put every single transaction or every single state update on chain because a lot of these updates are redundant. So for example, with trading, a lot of, during a day, you could have like, your portfolio could, if you're, I don't know, algorithm trader or a high frequency trader, your portfolio changes a ton. Like you could have 10 assets in the beginning, then in the middle of the day have 100 different assets, and at the end of the day have 20. You don't really need that entire story of having 100 assets in the middle to go on chain. You want just the final, the endpoints. And you can do a proof that that is the case on chain. Like I can prove that here's what I used to have on chain. Here's a commit to some prior state tree. Here's a commit to a new state tree. Here's a proof that what happened in between is valid.
Mm-hmm.
And this is useful for building an application, which doesn't need the data on chain. It just needs to be able to prove that all data is authenticated. Another example is key transparency. So if people are familiar with the internet, like SSL. Well, SSL is what ensures that your data, all your encryption data is kept private. There are these things called key transparency logs, which are basically just append-only logs that only Google gets to write to that secure a lot of this infrastructure. This is called key transparency. SNARKs are like, you could then put this on chain. Like you could have a blockchain do this. One problem is that you need to write every single update onto the chain, which could be expensive because this is this expensive finalization procedure that's being shared by many processes, by many different applications. You can instead just put root 1, like here's the old root. You can say here's a new root and a proof that this update is valid. So for your application, just securing the internet, you via this key transparency log, you now reduce the amount of the expense of updates because you put it on chain with proofs in between. And this is something that would enable getting more rapid key transparency updates, or like lower time to getting new sites to SSL encrypted. Which probably interesting for like Nishan.
Yeah.
Like what you're working on.
Right. And then so then one other question that I was just kind of thinking about, just about like general scalability with SNARKs. So like what we want in the end with these like blockchain financial platforms is to like reach the scalability and like people talk like TPS of like, I don't know, they always compare to like Visa, right?
Yes.
So I was just quickly checking, and like Zcash has a much higher TPS than like compared to Bitcoin, how people like to compare, but it's still not there, right?
Zcash has a high TPS. That's
no. Higher than Bitcoin, Not crazy. It's like 25.
Oh, okay.
Yeah, but like, so I guess that's the limiting factor. Like that's the metric in blockchain scalability, right?
Yeah.
So what do you think? Like,
ill-defined
what
metric,
is?
but yeah.
Yeah, true. But then so like almost a broad question, like, do you believe in like blockchain scale? Like, what are we gonna have to do? Like,
Yeah.
zk-SNARKs do these cool
Sure.
things, and like.
Let me go to the slide with scaling. Okay.
Yeah.
Here is the latest slide. Can I edit? Okay. So what's left is state size, I/O, bandwidth, and data availability. So let me draw some shapes. Can I change the color of this? Sorry, I just started using like Keynote today. I switched operating systems. Okay, so data availability solved by lazy ledger. Computational load, I think this is solved with SNARKs plus research for improving that constant. The 1,000 is a big number. And you can also we also have work improving, like in the space, lots of work coming up this year, improving the compilation from normal code to SNARK friendly code. So I think that part's gonna get even better. Plus, when we add like ASICs and stuff, it'll probably just go away. State size, there is a solution. It is called, not yet implemented because, or actually no, Coda is implementing this. When I alluded to, there's two things they integrate to get their good numbers. One of those was stateless verification. So what stateless verification is currently every full node, and the miner in fact, has to store the entirety of state, the 500 gigabytes. Right? So what you could instead do is have every light client keep a inclusion proof to their data. And then you can have them, like, whenever they submit a transaction, they include the inclusion proof to the data. And so then you've authenticated the input to your algorithm, the input to the transaction. Like, you're not having every node store that your balance is $5. You're having every node store the entire Merkle tree commitment of all balances. And then every transaction includes a proof that I had $5. Does that make sense?
Yeah, that makes sense.
So this is, I think, a great idea because it means that you've eliminated the state size problem.
Yeah,
but there is an issue for you've thrown a lot of work onto light clients. So this means that a light client needs to store an inclusion proof to every part of state they want to interact with, really. And so this could be bad. Like, suppose I make a transaction from my phone. So now I have to sync this to my laptop to then transact from there, like to get a new push proof of my balance. And there's a second problem with like, you have to update these inclusion proofs every block. So there's some things that mitigate this again. Like, there's this, you can switch away from a Merkle tree to a new type of vector commitment stuff, which requires some hardware, which executes on anything, but it's a bit slow. So you need some new hardware. This is called RSA accumulators, or vector commitments. And you need a new type of service provider called, like, the term, I don't think they have a good name yet. Essentially, they store the entire state tree. Like, you have one or two services, similar to like Web Archive or something, that just provide tons of data storage and will do inclusion proofs for everybody. But this could be wallet providers, and is a reason why wallet providers are getting paid. Like, so this is, I think, a very tractable problem. Consensus time is, you use proof of stake. This drives it down to like 5 seconds, which I think is, I don't know, might be good enough for finality.
Right.
And then there's some suggestions to use to get even better finality, like heuristic finality, by using avalanche-like techniques in between. I know I marked in red here that consensus time is like, gets worse with SNARKs. That was just if you do things naively. There's ways that we can probably do it better. So, and once SNARKs improve in time and we get like better parallelism, it becomes not a problem again. So I think this like sort of addresses all the scaling issues. So I do think the blockchains will scale very well, like once we get time to implement all of these things.
Well, yeah. So it's like, it still is like a big if, but like if these all like come true and like all these are implemented properly and they all find their way in one ecosystem, then we're good.
Yeah, well, I'm not sure it's a big if. It's just like, it takes time to build this stuff. I think it's really a time question. Like, the time is, will this happen in X years? That's perhaps a big if. Will this all come together? Like, it seems like all of the pieces are here, except maybe like bandwidth. This is the hardest because it's limited by physical pipes.
Right. Yeah, that makes sense. Okay, that's pretty cool.
Yeah, and there's tons of privacy as well that like can get added or is getting added.
By the obvious, yeah.
Like yeah, Zcash. There's similar that Zcash like, but for your computation itself, which is really cool. The paper is called Zexi, Z-E-X-E, and there's people implementing this now, like blockchainizing and productionizing it.
All right, I guess I have another question about just like SNARK development and like zk-SNARK development.
Yeah,
so
you
like
need more people.
Yeah, like say someone wants to like use zk-SNARKs in an application. How easy is it for them to use it? How easy is it for people to like develop almost SDKs to use zk-SNARKs? What are like the challenges for it? Like,
there are some SDK like things. Here's an OCaml one, which is I think the most built out thing. So if you can read OCaml, maybe this makes sense to you. I am told this is like normal OCaml. I've written Haskell, so this feels not that bad. But another thing is Zinc. I don't know if this has code examples. This looks a lot more like normal code.
yeah.
Wait, no, that's Spellman. It's not normal code.
Yeah,
This is normal code.
Got you. Yeah, I'm kind of wondering, like, are there any trade-offs that have to be made between like the ideal SNARK application or like SNARKs and what they are, like the theory behind them versus like when you have to implement one? Are there any differences, or like are we good?
So by implement, do you mean like implement an algorithm to be SNARKs, or do you mean
Or,
implement the proving algorithm?
I don't know. I don't exactly know what I mean either. Yeah, both. But...
Okay, so ideally as a developer, you want to be writing in the front end. You don't want to be writing in the back end language because that's roughly like assembly.
Right.
So the point they're making here is here's the assembly. Here is the not assembly. So you can write in these not assembly things, these nice front end languages, and then you compile it down into a SNARK. And you compile it down into the SNARK friendly language, the SNARK friendly assembly.
Right.
And so this induces overheads, right? Like you could always write you can always like hand write assembly, something that's like I don't know, 10% better or something. So it depends on the compiler overheads. These compiler overheads keep on getting better.
Okay,
so
that's cool. Yeah.
And eventually it should hopefully be equivalent performance in terms of that. Currently, I don't know, some overhead may or may not be significant. Who knows?
Cool, thanks.
Another thing is, like, I guess for writing the prover backends, what we write in theory translates very well. Like, in fact, most SNARK papers now come with implementations. And the only thing you run into is, a lot of times in code, you do something faster than what's in theory. Like what's in theory worked. You just then apply like math tricks or a lot of like custom things on top to get the slightly better performance.
Nice. Okay, that answers it.
Yeah. Like one example is, use an FFT. This is used in every SNARK that exists. Well, there's an FFT algorithm you learn in CS 170. The Cooley-Tukey algorithm where you use like you say fx equals g of x squared plus fx equals g of x squared plus x times h of x squared. A sort of a cool recursive decomposition.
Yeah.
It turns out that there are other decompositions that work better, like slightly faster, which matters a lot for your speed, but it's not a huge deal in terms of like mental abstractions.
Nice. All right. Yeah, that's pretty cool.
Yeah. So the way these things, SNARKs are very well abstracted. If people want to like get involved working on them, and they're also thanks to these like nice DSLs like Zinc, Snarky. It's not bad to write SNARKs either. Like to write applications that use SNARKs.
Nice.
Any more questions from students? If not, we will end the lecture a bit earlier.
All right, sounds good. Yeah.
Yeah, thank you a lot, Dev.
Yeah.
It's great
Thank you so
having
much.
you here.
Yeah.
Yeah, we'll be sending out the information about homework after the lecture, and the recording will be posted online.
All right. See you guys next week.
Yep.
Thank you.
Yep.
Thank you, Dave.
Thank you, Dave.
Take care of you guys. Take care of yourself.
Stay healthy.
Yeah, stay healthy.